So let's talk a little bit about some future directions. And here, what I want to do is to say, let's stretch our imaginations of where I think are some exciting opportunities for using geophysics. And here, most people probably joining this webinar are geophysicists and exploration geophysicists. And many of them may be oil geophysicists. We know that 75% of the world's oil basins show hydrocarbon seepage. In fact, only 11% of drilling on prospects without an associated seepage anomaly result in discoveries. In the Gulf of Mexico, for example, there's a lot of oil seeps. And so one technique used in exploration is to be able to sample these oil seeps or sample the basins to look for locations where these oil seeps are, because where there are oil seeps, there's probably bound to be hydrocarbons at depth. And so geochemical techniques are often used. This can again be laborious, very expensive, and even more exciting is the fact that we can look for microbial anomalies. And here again, you have to do a very tight grid to sample for this to determine these microbial populations that are capable of breaking down the hydrocarbons. And we've just showed you examples of how geophysics techniques can actually determine the presence of microorganisms. And I really think that there's a potential here to be able to use the geophysical investigations to determine where we have these microbial anomalies, and so we can optimize or reduce the cost of these microbial exploration efforts. And this is an example from an oil field in Sudan where we can see magnetic anomalies associated with oil seeps. As I've just showed you in the previous example, that microbial ion cycling can result in the precipitation of magnetite. And so here's a clear example then how we can use the geophysical techniques to look for these microbial anomalies. Another really exciting opportunity exists in looking for life in extreme environments. See, microorganisms, as I've already indicated, live in very, very harsh environments. They were our first organisms to colonize the Earth, and they've been here for a very, very, very long time. The oceans make up 70% of the Earth's surface, and it is known that there's more microbial mass in the bottom of the ocean floor than we actually find in the continents. But the nature of deep microbial life in the sea floor remains poorly understood just because of the vastness, and it's really difficult to get to these extreme environments. But it is important to be able to know who are they in terms of the microorganisms, what are they doing, how many of them are there. What I plot here in the right is a recent, really exciting study by Suzuki et al. 2020. So what they show is that they document dense clusters of microbial communities within the cracks of ancient clay-rich volcanic rocks of the ocean crust, as deep as 100 meters beneath the seafloor. What they found is, surprisingly, what they found is microbial communities reaching up to 10 billion of bacterial cells within these cracks in the rocks. And what you can see here on the right side of the image is these little green blotches are actually the microbial cells. And I really think that this is some really exciting potential for us to be able to use geophysics to be able to integrate geophysics with some of these environmental microbiology studies. The last example that people typically are always wanting to find out, so can we use geophysics to search for life on Mars? Finding potential life-bearing worlds is NASA's next big challenge. And we're looking for candidate planets that have to be just right. And these are candidate planets that would have conditions very similar to those on Earth. We know that if there's life on Mars at all, or in any of these planets, it's most likely going to be microbial. That's because they can withstand, or they can live in very harsh environments. And what we now need to do is to look for the biosignatures, which is the records of microbial activities that are left in the rock. The challenge, of course, is to find unmistakable signs of current life. And so there is a potential then to use geophysics, to be able to use geophysics to search for life. We've had several robots that have gone to Mars, and the most recent one, which is InSight, is actually acquiring geophysical data. But in this case, the geophysical data they're trying to acquire is the seismic, or I think there's a heat probe to look at the subsurface structure. But we think that there's a potential to use geophysics differently, not necessarily to only look for structures, but to search for biosignatures in Mars. As I've already showed, from our geophysical data, that interfaces are prime areas for us to look for these signs of life. So some key takeaway points here is that microorganisms do in fact leave their biosignatures in their environment that can be measurable by a variety of geophysical techniques. And what we've demonstrated that we've not had to do anything different with these techniques. We've just used conventional off-the-shelf tools, and we've been able to demonstrate that these biosignatures that are left in the rocks can be imaged using geophysics. These biogeophysical tools can identify biogeochemically hot zones, which would make it a lot easier for geomicrobiologists to study and better understand. And that we can use geophysics in a variety of ways to monitor remediation efforts, to look at microbial enhanced oil recovery, and even for resource exploration, as I just showed you the example for microbial oil seeps. But to me, I think the most exciting potential really is to be able to use the geophysics for investigating life in extreme environments. So this brings us to the end of the presentation, and thank you for listening, and I will entertain questions at this time.